Hi, I'm Mark Seacrest. Welcome to this last session that's part of our Climbing the Peak series designed to teach you the basic elements that you'll need to know in preparation for your Couchbase Associate Java Developer certification. This series of sessions was really designed to help fast track you and provide a study session in preparation for the certification that we announced at the conference. And so hopefully you found the rest of the topics very interesting and helpful. And we're going to conclude this section with ensuring your application makes it to the top, meaning we're now going to begin talking about topics that will help kind of bring some final capability to your application, specifically in as much as you start thinking about your application moving towards a production environment and so on. All right, so let's start with just kind of understanding the challenge that we have in front of us. Some things to think about as you're moving your application into deployment. So if you remember our discussion of how we stored documents in the earlier sessions and how we fetched and updated and then stored those documents, think about this. What happens if we have a document that's perhaps a very large size and we want to make an update to one of the attributes? Maybe we really only want to update one of the attributes or a couple of the attributes of the document. Is it worth bringing the whole document from the server, making the changes, and then storing the document back? Maybe that performance impact is a little more than you want to pay just to make an update on one element. So we're going to talk about how to solve that problem using sub-document operations. Next, what happens if in a multi-user environment, you have multiple users who are attempting to update a document at the same time? This is a real scenario that could occur in cases where you have multiple users who are using the same application and potentially, in some cases, maybe making changes to the same document at the same time. So how can we mitigate that particular risk? And finally, understanding the nature of deploying applications into a production environment means realizing that in production environments, we often have clusters of Couchbase servers, and the data is actually distributed and potentially replicated as well as persisted. And so given that, how do we take those things into consideration? How do we factor that in and potentially maybe change the way in which we perform mutation operations, keeping in mind the fact that these things exist and how we might want to take advantage of or take more control of the storage process that's related to performing a mutation. So we'll conclude our this session with a little bit of a discussion of how we can do that for our various mutation operations. Regardless of any of these challenges that we've discussed, realize that the Couchbase Java SDK is able to handle those scenarios. We've got the capability in the SDK natively to be able to solve these and many more problems as well. So the goals of this particular session will be to understand a couple of new methods on the collection called LookupIn and MutateIn that'll allow us to work with subdocuments. We'll talk about locking strategies, pessimistic and optimistic locking. And finally, we'll talk about the Java SDK and how we can actually take more control when we're performing mutation on the storage behavior and what might happen behind the scenes on our Couchbase servers. Let's go ahead and get started. Okay, to begin with, let's start by looking at this JSON document that we have in front of us. This is actually something that we've talked about perhaps a couple of different times if you have attended the different sessions that we've been presenting. This is a playlist document that's part of the Couch Music data set. And in this particular form of the playlist document, we have a couple of different interesting things here. We have an owner identified as a complex object. So that's modeled as a nested object inside of the JSON document. What's also interesting about this is that data is duplicated between information found here in the playlist and information that is found on the user profiles object or the user profiles document. The reason we might choose to do that is that we have ready information about the user or the owner that can be displayed when we pull up a playlist. So we can go in and get a list of playlists for a given user, and we immediately have the user information. So there's some interesting use cases for that. And so that's how the data has been modeled. Notice down below that we also have the tracks element, and tracks is made up of an array of elements. So if you think about how you might perform operations on that, what we've seen in the past has been this ability to do a key value operation. That is, I can perform a get, retrieve the entire document, make changes to the owner or other attributes, maybe add an element to the tracks and so on, and then I would store that entire document back. With subdocument operations, we can actually surgically go in and make changes to the sub-elements of a document without having to fetch and change the entire document. We can go in and just change the first name of an owner, or we can change some other element if we choose to as well, using subdocument operations. We can also use subdocument operations to perform non-mutating type operations where we can get an element or a sub-element. We can check for the existence of an element and those sorts of things. So that's kind of the motivation for being able to do this sort of thing. And so I want to introduce you to two methods that are also found on the collection class or the collection interface called LookupIn and MutateIn. So the pattern of these is very similar to their key value corresponding methods. The difference here is that the second argument is going to be a list of operations that are expected to be performed. And we'll see there's some variations in that depending on the operation that we want to perform. But essentially, we have two categories, LookupIn and MutateIn. And we can think of these as being grouped into non-mutating and mutating operations, essentially. So a couple of things that you should note right away about this is that we can perform, on a given document, we can perform one or more subdocument operations alongside of a set of options that apply to the entire set of operations that I'm going to execute. So that's the way to think about these operations. A little bit different than you might be used to thinking about in terms of typical key value operations. But once we get into it, you'll see that this is actually a very easy to use mechanism. It's just requiring a slightly different way of thinking about how to use them. All right, so that's the setup for this whole discussion. Now, as we move into this, let's take a look at the details of the LookupInSpec and the MutateInSpec. Now, LookupInSpec and MutateInSpec are classes that contain static methods. These static methods are the mutating or non-mutating operations that can be performed. So LookupInSpec has a set of static methods called get, exist, count. MutateInSpec has a set of static methods called insert, upsert, remove, replace, and so on. So that's basically how these are defined. And you'll see in the corresponding code we have on the right that we've essentially taken the liberty of performing static imports to just bring in all of those operation definitions by just doing a static import of everything that's in lookupinspec.star and mutateInspec.star. So that basically imports all of those static methods. And we'll see that later that actually simplifies how we will build our various operation definitions. Okay, so the thing that we're looking at here is the LookupInspec definition and the MutateInspec definition. Keep in mind that these are a list of operations that can be performed for their corresponding LookupIn or MutateIn method. Okay, now each one of these methods, whether it's a get, exist, the insert, or so on, it's going to have a set of logical parameters that can be passed in. So if you think about a get, for example, a get would typically say, get me the document if we were talking about a key value operation. So you just pass in the key or the ID of the document. In this case, we've already specified the key as kind of part of the LookupInspec. So what do we provide to the get? We would actually provide the sub-element, the sub-document element that we're interested in getting. So we're not returning the entire document, we're returning the element that represents the string that for the value, we're returning the value associated to the string, which is the name of the element I want to return. So basically that's what that's doing. So there's a set of operations. We can do a get, which is what you might be familiar with. We can check for the existence of an element. We can count the number of occurrences of that element, perhaps within the document. So, or number of values. So I might, for example, be able to check the number of elements in the array for the tracks element, for example. So we could count that and see how many elements there are and then determine what we want to do from there. Then in the MutateIn, we have insert. So if you think about an insert typically would have a key and a value. But for this subdocument insert, it's going to be a element ID and a value that we're going to pass in. And for upsert, same thing. And for remove, we would just remove the element that's specified by the string and so on. So that's basically how those work. Now let's transition over and take a look at the code and see how these actually work. So the thing to keep in mind here is that we're passing in an array. There's a lot of ways to build up this array of commands. I'm going to show you kind of the longhand way to do it, and then later we'll see that there's a more shorthand way to do things where we just build all the entire command inline. Now, the advantage of that is it's a bit simpler to write. The disadvantage of it is that if you're newer to this sort of thing, it sort of is difficult to understand the different pieces and distinguish what's going on. So I've chosen to sort of list or show the individual steps just so you can understand the building blocks. So what have we done here? Well, we built a list of type mutate in spec. It's an array list. And with that array list, I'm going to add an element from the mutate in spec. In this case, I'm adding the replace. Now, because I did a static import, I technically don't have to prefix the replace with mutate in spec. Mutate in spec is kind of the longhand way to do that. So I'm basically saying mylist.add mutate in spec.replace, and then the element and the value that I want to replace. So you can kind of see how that works. So I have one element added to the array, and then I perform the mutate in operation, where I invoke the mutate in, specifying the document ID, and then the list, which contains the operations that will be performed against that document. So hopefully that makes sense, kind of helps you understand how that the building blocks kind of build up. Now let's look at a little more complex example. Only more complex in that we're going to build this one in a inline approach. We're just going to build all the pieces together in more of a shorthand approach, and you'll see that we can do much the same thing. In this case, we're performing a lookup in. And instead of first building a list and adding to the list and then adding that list as part of the lookup in command, we've just simply inserted an arrays.asList inline. So essentially what that allows me to do is just dynamically declare a set of elements that will be added to the list. These elements will be the various operations of the mutate in spec, or in this case, the lookup in spec. And so we add the elements, and then we pass that in as the second argument. So I'm performing a lookup in method call with the ID for the document and then a list of operations. In this case, one operation, which is the get. You with me so far? Okay, let's look at the next example. All right, so here's a mutating operation, very similar thing. We're doing exactly the same thing, except in this case, we're performing a replace again. And in this case, it's very similar to the first example I showed, except now it's entirely in line. And lastly, I'm going to show you how to perform an array list insert. So again, imagine that we had that tracks list and I wanted to add a new track to the playlist. How would I do that? Well, I have some track defined as a track ID, and I've just arbitrarily declared it as a string. And then I do a mutate in, the ID for the playlist having the tracks that I want to amend or change. Then I do a asList array insert. So remember, array insert is one of the methods that's found on mutate in spec. So it's one of the operations that I can perform when performing the higher level mutate in operation. Now, because tracks are an array, I'm actually going to pass in an array as the second argument, which of the array insert, which is the value. Okay, so I'm going to pass in, rather than a discrete value, I'm going to pass in an array. And that array is going to be inserted. And that means I can actually insert more than one element into the track. So if I wanted to add two tracks at the same time, I could do that by just putting two elements into that second array. So it's very streamlined, and you can sort of see that it's both easier to write, but slightly more difficult to follow what's going on in the code unless you really understand what's going on, which is why I chose to kind of break it out initially. So hopefully all of that makes sense. Now, the last thing that I want to say is this. When we build up a list of commands that we put into the list and we submit them, we have to understand that those are executed in an atomic fashion, meaning that every operation that's in the list either succeeds or fails together. There's no way to distinguish or separate those two things out. They must both succeed or they must either succeed or fail. It's not the case that you can have part of them succeed and part of them fail. So it's an important thing. So it's kind of like a transaction, but it's not really a transaction. It's all operating on the same document. Okay, let's take a look at the results that come back. So just like we can insert the values, or we can perform operations as an array of operations on the document using mutate in or lookup in, we also can process the results as an array. And so the order that the commands come in is the order that the values will be returned. That's an easy way to think about it. Okay, so essentially what that means is that the lookup in results, because I submitted, because the second argument is an array of operations. In this case, I'm performing a get, well, I'm performing an exist and a get in that order. Then we will get results back for each one of those operations also as an array. So how do we get those values back? How do we properly specify them? Well, that's the interesting part. And so I want to show you kind of how to do this. And I intentionally switched the order of these just so you would kind of see what we're trying to do here. So what was the first operation I submitted to the list? That was the exist operation. And because of how arrays work, as you probably know, position 0 is going to be the first element and position 1 is the second element, and so on. And so it's important to keep that in mind as we move forward, because that's going to affect how we get the results back. So the get operation was the second operation I submitted, so it's in position 1. So if I want to get the result of the get operation, I would do a content as. We saw that in the key value operation. If we wanted to get an object back and have it converted into a domain object, I could do a content as, but because we're getting the results back as an array, the first element has to be the position in the array. So content as, first element is which position, which element of the array. The second is what's the type I want to return that as. And so I'm simply saying, give me back the second element of the array as a type obj, whatever that object was. Okay. Now, in terms of the exist would return a Boolean, true or false. So I'm always going to convert that one to a Boolean. And because that was the first operation submitted, I would use position 0 to get the result of it. So again, hopefully that makes sense. It's just corresponding. You would align the results to the order the objects, the operations were submitted, and that would be how you get them out. All right, let's move to locking strategies, our second issue that we talked about with respect to our production operations. Okay, again, the use case behind this is to understand that we have situations where when we deploy this into production, the anticipated application behavior is that you will have multiple users accessing the data, reading the data, perhaps changing the data. And if you have users changing the data, there's a risk that two users could, in fact, change the same data. Now, that's potentially a slim risk, but it is a risk that you have to take into consideration and make the appropriate, take the appropriate precautions. So if that is a concern, there are two strategies you can employ. One is called pessimistic locking, and the other is optimistic locking. And you can kind of imagine, just thinking about the terms pessimistic and optimistic, what we're trying to achieve. Pessimistic locking assumes the worst case scenario and simply says, I assume that somebody's eventually going to try and write this. So rather than taking a risk, I'm simply going to lock the object for a period of time, perform my operation, and then release. And in the case of optimistic locking, we're kind of saying, I assume that most of the time this is going to work, but on the chance that it doesn't work, I am going to build in a mechanism to catch the case when it fails and take some sort of action to mitigate that problem. So we're going to dive into those two things, optimistic locking and pessimistic locking. The thing to understand about optimistic locking and why it's probably the more interesting approach is that there's virtually no performance cost associated with it. There's very little cost to having optimistic locking, because really all we're doing is performing an extra check on top of everything. We don't insert the sort of heavyweight exclusive lock operation over the top of things, which can potentially bottleneck updates and changes in the application. All right, so what's behind the optimistic locking? Typically in optimistic locking, we use some sort of a versioning object to help us understand if the object we're intending to store has been subsequently changed by somebody else. And the way we do that is through some kind of a version check. And this one mechanism that can be used to do this is called a CAS, or compare and swap. And it's the mechanism used by Couchbase. It's a mechanism that can be used for optimistic locking, and that's basically what we do. So a couple of things to know about the CAS. The CAS is maintained by Couchbase. It's part of the metadata associated to every document. So that means that when you do a store of a document or an update of a document, you are actually modifying the CAS value. Well, I would say specifically Couchbase is modifying the CAS value and automatically incrementing it. Okay, automatically changing it. I'll say it that way, just so it's perhaps a little more correct. All right, so Couchbase is taking care of storing that. You have access to the CAS value. You have access to the CAS value two different ways. One is there is a nickel query you can perform to actually get that element. And I've showed it to you here, but probably a more common way if you're a developer is that you have access to the CAS value whenever you perform a get operation. So when you do a get, one of the components that's available in the get results, besides the value itself, is the CAS value associated with that document. So that's interesting because that means we can actually keep that CAS value. And the basic pattern we'll use for optimistic locking is that I'll get the CAS value on the read, I'll perform the update of my document, and then when I go to store the document, I'll also provide that CAS value that I had on the beginning. And the idea is that if I'm storing a document and nobody has changed it behind me, then the CAS value that I'm providing is going to match the CAS value that's currently associated with the document. And so that storage will succeed. However, if somebody had subsequently made a change to the document from the time that I did the get and the update, and then I went to store, that means the CAS value in the database is actually going to be different. And we get what's called a CAS mismatch. And so Couchbase in the SDK will throw a CAS mismatch exception when that occurs. And so that's why we would supply that extra argument. So a couple of things you should know about this is that it's actually really easy to implement this pattern in its basic form because all of the elements are there and available to you. So a couple of changes that we've made to the code that we may have seen in the key value operations, the very first session, is that when I perform my get on the collection, and I have my get result, not only would I get the object itself, the value, but I would also get the original CAS value. And I would just keep that. Hang on to that CAS value. And then I would then use my replace options. And we'll see that on my replace options, there is a method called CAS. And it's the mechanism that allows me to supply the original CAS. So semantically, what I'm basically saying is I want to replace the document whose ID is whatever the ID is. And I believe the CAS value is whatever the value of that CAS value is. And if it turns out that the CAS value does not match the one that's stored in the document, that means somebody's changed it and we would throw the exception. And so this is where the SDK would actually throw the CAS mismatch exception. Okay, so the thing to understand is replace options and remove options both have the ability to supply a CAS. One thing to note is if you're interested in optimistic locking, the upsert does not allow you to provide a CAS value. So if you're interested in optimistic locking, you should not use the upsert. You should use the replace instead. So replace and remove basically are the ones that you want to pay attention to when you're specifying the CAS, because those are the two where you could potentially have a collision of an object. All right, let's look at one more example here, and that is how we would actually implement the entire pattern. So what I've told you so far is that we can potentially throw a CAS mismatch exception, and we assume that in most cases the operation should succeed, except on the rare occasion when we might have had some sort of a collision where somebody changed the document and therefore the CAS value associated. So what do you do in that kind of a scenario? And how do you sort of recover from that and come up with a success outcome? And that's kind of what this pattern is all about. It's a retry pattern. And basically the idea is we set up some kind of a looping strategy. Lots of ways to do that. This is one example I'm going to show you. It's basically a looping pattern where I'm going to loop over the basic operation, which is the get the object, including the get result, get the original CAS. I'm going to make the change to the document. In this case, I'm updating the password with a new value. And then I'm going to attempt to replace it, supplying the original CAS. Now, if everything works and it succeeds, I need to have a way to break out of the loop. But if it doesn't succeed and it throws a CAS mismatch, I need to have a way to recover, reset, and retry. That's basically the pattern of the retry pattern. And so you can see the mechanisms here. Again, I want to stress that there are many ways to solve this problem. This is a simple way for you to understand how you might implement a looping retry pattern. A couple of things you have to solve for is, how do I know if I get a CAS mismatch? So make sure you catch the CAS mismatch exception. The other is, what do I do if I succeed in storing the object? That means that there was no CAS mismatch. So how do I break out of the loop that you've got set up? And then the third thing is, assuming that I do have an issue, should I wait a period of time? What should I do before I go back and restart? So those are things that you'll all have to think about as you're building your own implementation of this. This just basically illustrates the core concepts that I want to stress with respect to the optimistic locking and the retry pattern. All right. Again, I want to mention that optimistic locking works with subdocuments. So just like there is in this example, in the prior example here, we were using the replace options and setting the CAS. In this case, we're using the mutate in options and setting the CAS value on that. Now, keep in mind, that's going to apply to every operation where a CAS makes sense. Optimistic locking makes sense. So in this case, we have one operation called replace, and we're performing that replace and supplying the mutate in options, which applies at the document level, not at the element level. So it's an important distinction. Even though we're performing subdocument operations, the mutate in options actually applies to the entire document and the set of operations with respect to that document. So it's important to keep that in mind when you use this particular approach. The point I want to make is that this works just as well for subdocument operations as it does for key value operations. And the last thing I want to talk about is pessimistic locking. Pessimistic locking, again, is the approach you would use in the case where you wanted to take a bit more control over the set of operations and perhaps have a higher degree of assurance that when you're performing an update, that nobody else can make an update. And so we're going to use a similar mechanism. We're going to use the CAS, but we're going to use the CAS in a slightly different way. Okay, so look at how we actually go through this process. The beginning begins just the same as optimistic locking until the point that we're getting ready to perform the operation. And so you can see that what we've done is, when we did the get of the object, we did a get and lock. And we specified a duration to lock for. So in this case, we're locking for 20 seconds. And that means that in the space of 20 seconds, I have 20 seconds essentially to make my change and store the object. Okay, and then I'm out. Otherwise, the document gets automatically unlocked. And that's the important distinction here, is that with optimistic locking, we lock for a period of time, but we don't want to run the risk that you lock it and then go away and forget that you locked it, and then you have some sorts of issues. So Couchbase automatically just limits the time that you can lock to 30 seconds maximum, but you can have it be less than that if you want to lock for a shorter duration. So the difference here is, instead of using the get, we're using get and lock and supplying a lock duration, which gives me the object. And then I perform my update, and then I go ahead and do a replace, supplying the CAS value. The distinction here is that I would not typically expect to get a CAS mismatch. It's not the reason I'm supplying the CAS value. I'm supplying the CAS value kind of like a key. That key allows me to unlock, remove the lock from that particular object that was originally locked earlier. And so that's kind of the thing you need to think about when you're using pessimistic locking, is that it acts more like a key than it does a key to unlock the lock, than it does some sort of locking or version validation or that sort of thing. Now, a couple of things I want you to understand about locking and unlocking. When you perform a replace and you supply the CAS value, it will automatically unlock the object. However, if for some reason you chose not to update the object and you wanted to unlock the object later, you could just simply perform an unlock, in which case you would just supply the unlock method call, the ID of the document you're unlocking, and the CAS value for that document, and then you can unlock it. So there's really two ways to do that, is the point I want to make here. All right. And that leads us to our last topic, which is durability options. Now, in order to help you make sense of this, I want to step back and talk a little bit in more detail about how Couchbase actually stores data inside of its buckets. So what we've talked about to date has been that buckets are the place where we store our documents. Technically, we store them in collections, which are stored in buckets, but under the covers, it's a bucket that actually stores the data. So the question is, how does Couchbase actually store the data? And how does it manage storage of data over a number of servers using a mechanism called sharding? So I'm going to introduce you to that topic, and that's going to help us understand why it's important to understand durability options. Okay, so a couple of things you need to talk about is you need to understand that Couchbase has the ability to store replicas or copies of the data for fault tolerance. That's a really important thing because when we're storing our data, if perhaps for some reason we lost one of our servers in the cluster, that would potentially mean we lose our data unless we had a replica. So replicas become very important in a fault tolerance scenario. The second thing you need to understand is that if you're using a Couchbase bucket, Couchbase buckets are always persisted. And so there's a persistence behavior that's going on behind the scenes, and perhaps you want to actually take more control of how that persistence process works. And so we're going to talk about that element as well. And then the last thing you need to understand is that you have control over the behavior of how storage works in the context of buckets that have replicas of data and buckets that are persisting to disk behind the scenes. So very important concepts to understand. So with that, let's go ahead and dive into this last topic. Okay, so basically, whenever you are storing data in buckets, you need to realize that Couchbase actually potentially breaks the bucket into these components called shards. Well, let me step back and talk about it in this way. When you have multiple data nodes in your cluster, your bucket actually is broken up into collections of data that are stored on each server. The way in which that's actually done is that we break up the concept of buckets, and we actually introduce this idea called virtual buckets or V buckets. Okay, so the important thing to understand here is that every bucket is actually broken into 1,024 virtual buckets, sometimes also known as shards. Shards is a common industry technique for what we're actually doing here. It's essentially breaking the logical notion of a bucket into physical buckets where the data actually sits. So that allows us then to take those virtual buckets and distribute them across all of the servers that are acting as data nodes in the cluster. So that's kind of how we got to this sort of picture where we had a bucket that's actually divided across servers. When that same bucket is hosted on all of those servers, the way we accomplish that is by way of these virtual buckets. So technically speaking, then, your data actually lives in a virtual bucket, even though the way that you access the data is through the bucket. Couchbase knows how to take your key and locate the appropriate virtual bucket on the appropriate server and return the data. So you don't have to worry about that kind of level of detail. The important thing to know is that Couchbase takes care of all of that for you. It will automatically shard the data across all of the data nodes. If you add nodes or remove nodes, it will manage the storage of those of that data and the movement of the virtual buckets from one server to another automatically for you. So the advantage of this is that it gives us a very easy mechanism to add a horizontal scalability by simply adding additional servers. You add another data node, that gives you another server on which to distribute the buckets. And so those virtual buckets get further distributed across all the servers. And that's essentially how we get the scalability that we want to have with Couchbase. So what does that mean to you as the developer? A couple of other things I want to introduce. There is the potential that you can have a replica. And in fact, if you looked at, I think in the first session, we might have talked about this a little bit, or if you go through the course, you'll actually see during the setup, when you create a bucket, you have the option to determine whether or not you want to have your bucket have a replica. By default, when you create a bucket, it will automatically be set up to have one replica. And if you have more than one data node in your cluster, it makes sense potentially to have more than one, or to have at least one replica. And so that's why we have that enabled by default. If you're running on a single node cluster, then you really should turn that off, because you get no benefit. There is no replica really to be had, because there's only one server hosting your data. But in a multiple node cluster, whether it's 3, 4, 5, or way more, you can divide your system up and actually have, for every bucket, you can have a replica of that bucket sitting on another server, which basically means that if you lose one of your servers, if that server goes down, then there's a replica that Couchbase can defer to. Now, one of those will always be kind of the primary or the main bucket. The other one will be standby. You can read data from it, but you would never update it. It would just be sitting around as a warm standby, waiting to be kind of activated if you ever had a failover scenario. So that's kind of important, because when you think about how data gets written, not only is it going to be written to the first bucket, the primary bucket, but it's also going to be replicated to the redundant buckets. What does that actually mean when you're writing data? That's an important thing to think about. The other thing that you should be aware of is that when you're writing data to your buckets, behind the scenes, we're actually asynchronously writing that data out to disk, which means after a period of time, you can be assured that if you brought your cluster down, you could actually bring the cluster back up and have it read that data back in, and it would automatically repopulate your bucket with the data. So we have that degree of redundancy as well, so that we can restore the data on a shutdown and a startup. Okay, so those two mechanisms are important to understand, because we need to think about what happens when you write data. When you write data to a bucket, it will immediately, by default, acknowledge as soon as it writes to the bucket, and then behind the scenes, it will replicate if it needs to, and then persist to the disk as it needs to. If for some reason you want a higher degree of assurance that you've actually written the replica or written to disk, you have the ability to specify that through these durability options. And that's kind of the point of this whole discussion, is to help you understand that you may want to take more control over the write process and actually affect the way durability works for some percentage or some part of your application. So I'm going to teach you this little concept, because it can help you if you're making decisions about, do I want to take more control over the data that's written, and make sure that before I return from a write, I actually get that replica written as well, or perhaps replica written and persisted to disk. So how do we control those behaviors? There is a durability option, and that is something that can be supplied as part of your replicate, upsert, insert, and all of those operations. You can actually specify a durability option. Durability is one of the methods that you can specify. So the important thing to understand is the behavior, how this works, changed a little bit from earlier versions of Couchbase, and then beginning in 6.5 and forward, Couchbase actually built more of the, I would say, the ability to manage that capability under the covers. So in the earlier days, you actually had to take more control over discrete aspects of that writing. Now, essentially, what we have is a mechanism that allows us to simply say, when we perform an operation, here's the behavior that I want, and then Couchbase under the covers will make sure that it happens the way we request. And so we've deferred more of that responsibility to the underlying Couchbase server, and the SDK really only needs to pass the requested behavior on. So the example that I'm showing here is that when I perform my upsert, part of my upsert options allows me to change my durability to something called majority. What does that mean? It means we're going to persist to a majority of data nodes. When we have replicas defined, that means we'll try to persist to a majority, and that'll guarantee that if we have a failure, we have somebody to fail over to when that data is needed again. We'll have somebody else that's holding that data. Now, there's different levels that we can specify. The default, the one that you get if you don't say anything, is called none. That basically means I'm going to write it to the node that's the primary node, and then I'm going to return, and I'll let the replication and the persist to disk happen behind the scenes automatically, and I won't worry about that. I'll just let Couchbase take care of it, and I'll trust that it happens and everything's going to work. But again, if you want more control over that behavior, you can change the durability level, and you can set it to something higher. So these are increasingly higher durability levels. It's important to understand that the higher the durability level, Of course, the higher your degree of certainty that you're going to succeed in writing and having that high availability and the persistence. However, you're going to give up some performance. So there's a trade-off between your confidence or your security in getting that data written and the performance cost. And so you're always going to want to balance those two things off. This doesn't come for free, which is why the default is a fairly sensible default. Setting the default to none and just allowing Couchbase to do the right thing behind the scenes is probably most of the time what you want. The important thing to understand is you do have control. You should use that control with caution, but Couchbase actually does give you a fair amount of control over that behavior. And the behavior is persist to majority means write to the majority of the nodes if you have more than one replica. Majority and persist to active means I'm going to write to the majority just like I had before, but in addition, I'm going to wait for writing to the active disk. Okay, so I want to make sure that not only do I get a replica made, but I'm going to write it to disk before I return. And then the last one is persist to majority, which is write to the majority of the nodes, and persist to the majority of the nodes. And as you can imagine, the more integrity that you're requesting before you return, the higher the cost because the longer it's going to take. So that means every write operation is going to take more time. Now, I'll just say that I have talked to customers before, and when mentioning that risk, they will say, it's okay because it's important to have the writes have a high degree of integrity. I read more than I write. So when I do a write, I want it to be right. I want it to be safe. And I'm willing to pay the performance price because I don't make those changes very often. So, I'm not saying that it's always a bad thing to do that. There are some cases when it makes sense to do it. I'm also not saying you should always persist to the highest level of durability because there's a cost associated with that. So you're always going to have to kind of assess your needs and make a decision as to whether or not you want to change that level. But this is the way you would change that level if you were going to do so. All right, and that brings us to the end of this presentation. Now, we've covered a lot of different things. We've talked about subdocuments. We introduced the idea of lookup in and mutate in order to access and modify subdocuments. We introduced the idea of locking strategies and the choice between optimistic locking and pessimistic locking, which are two ways to solve the multiple access or the concurrent access of data. And last, we've introduced the idea of persistence and replicas, and I've shown you how to tune or tailor your durability options to take into consideration what might be happening behind the scenes in terms of writing to multiple data nodes for redundancy, and then also persisting to disk. Now, all of these are kind of what I'd call production grade concerns. They're the kinds of things that once you get past your basic implementation, you start thinking about wanting to do these things that are really a lot of times about, I would say, higher order kind of capabilities. As you're heading to production and putting kind of the production polish on your application, these are the kinds of things you'll typically think about. Now, one final thought I wanted to introduce is Couchbase recently introduced the transaction SDK. So as of Couchbase 6.5 and the 3.0 SDK, we now have support for atomic transactions over multiple documents. Now, that's something we didn't talk about in this session, but transactions are an interesting way if you want to perform all or nothing semantics of some kind of operations between multiple documents, then transactions are a way to do that. And so you may want to take a look at the transaction SDK if you want to learn more about kind of performing atomic operations across multiple documents. All of these things, by the way, everything that I've talked about can be found on that SDK page that I introduced you to in the first session, which is the SDK getting started. If you go to the Java SDK and you just kind of look at the first couple of introductory topics, they talk about such things as subdocuments, replicas, locking strategies, and so on. There's also a section on transactions. The transaction API is actually a separate API. So if you are going to use transactions, the Couchbase transaction API, you'll need to add another dependency to your project to bring that in. But that's really all there is to it. And then you can begin performing transactions. All of that's covered in the documentation. This is just an introduction to all of those concepts. So again, thanks for attending all of these sessions. If you attended all of them, then we hope that they were valuable to you. We hope that they help you prepare for your Associate Java Developer certification. We talked about climbing the language peak. That was the topic I talked about yesterday, which was introduction to the SDK. Also yesterday, we talked about data modeling, climbing the data peak. Then earlier today, we had a session on climbing the query peak, which is nickel querying, and then we concluded with this session. So all of these, again, were designed to help you prepare and fast track and perhaps fill in some gaps on some of the questions you might have with respect to developing with the 3.0 SDK and preparing for the certification. I will say the certification is it's an exciting new addition that we've added to our portfolio. It is a proctored certification. If you want to know more, you can go to our website at couchbase.com/academy and follow the links to certification. There's a ton of information there now about what to expect. There's links to get access to the study guide. And so you can learn more about how to prepare for the certification and what to expect from a logistics perspective and all sorts of things like that. So I encourage you to go take a look at that as you begin thinking about sitting for your certification. So thanks again for attending. Hope you enjoyed the conference. Hope you enjoyed these sessions. Thanks a lot for your participation, and I hope you found this valuable. Wish you success as you get out there and start developing with the SDK, and as you potentially prepare and sit for the certification. See you later. Bye.